Record. Okay. There we go. Okay, so. Oh, yeah.
For homework, I didn't get any assignment for the peer review for homework 6.
For homework 6?
Yeah, for the...
Oh, okay. Yeah, I haven't actually taken a look at the homework 6s yet, so if you didn't get a peer review one, I'll end up doing it.
Okay.
So that's fine. And since I haven't looked at them yet, that's why there's nothing up,
Okay.
but I'm probably going to be able to do it this weekend.
Okay.
I've just been pretty busy because, yeah, I'll start with upkeep stuff rather than going straight into lecture. So I'm most of the way done with putting a lecture together for next week. I've gotten all my stuff together for the broom package, which ended up being a lot lamer than I thought it was going to be, but it led me to something a lot cooler, which is the GG Effects package. Then the GG Effects package led me to an entire family of packages developed by the developer of that, which are totally cool, which is called the SJ Plot, SJ MISC packages. So we're going to get into that kind of stuff. It's super cool for displaying like results and things like that, which is basically what it's all about. I also wrote a package to do to generate counterfactual data to do modeling stuff, the kind of stuff people do in like the MLE class. If they want to do that, you want to do counterfactual analysis stuff like that. So I wrote a whole package. It works really well, everything like that. As soon as I got done writing it, I discovered a package that does a really good job of doing it. And so I'm going to teach that instead of the package that I wrote. This inevitably happens anytime I find like something, I come up with something complicated, can't find a package to do it. I write my own, and in the process of doing it, I realize exactly what's involved. Then I learn exactly what I need to search for, and I find somebody else has done it much better than me. So often do a better job Googling before you start writing something complex. I'm going to teach that, but I mean, the package that I was working on does a few things that doesn't do, like actual parameter simulation and stuff, which is what like Chris Adolph's SimCF package does, but whatever. This is good enough for us. We'll talk about some of that stuff, calculating marginal effects, plotting things, so basically replacing your regression tables with regression plots. But we're also going to show how to do publication-ready regression tables and all that kind of stuff using some new packages I just discovered that work a lot better than what I've been using up till now. Totally sweet. I haven't gotten around to adding the advanced data cleaning stuff yet, but I'm hoping to get that stuff in time, at least a few slides on it. I already have like 45 slides on the stuff for the Broom and GG Effects for next week, because I ended up just finding new stuff and being like, this is totally awesome. So I spent like all day yesterday on it and the day before, and then like, yeah, anyway. So that's good news. It's going to be a good lecture next week. Let's see. So some people have had some problems with the geospatial homework. A lot of people have had problems, and it's because of something that is not uncommon to happen in R, and that is when when a package that relies on another package is out of sync with changes that have been made in that package. So ggplot develops pretty continuously. New code is put into it, things are modified on a pretty steady basis. So what happened in ggplot 2.2.1 is they changed the names of a few arguments and the way some code works for particular types of plots. Well, the result of this is that it fucked the ggmap package. It doesn't work. So this happens. ggmap is in the middle of being tweaked to make this stuff work, but it's taking a little bit of time because ggmap has a much smaller number of people working on it than ggplot. This is the kind of thing that usually, when a major package does major changes, like ggplot, you end up with a buffer of a week, 2 weeks, sometimes a month, where sometimes packages that rely on it don't work well. We just happen to be right in the middle of that because ggplot 2.2.1 just came out like a week or 2 weeks ago or something like that. We're currently sitting in the middle of that. It sucks. I gave you a 1 week extension, hoping that most of that stuff will be worked out, or at the very least you can use the solution I sent out on the mailing list. The solution I sent out on the mailing list is to temporarily downgrade your ggplot back to 2.2.0. It will work perfectly if you do that. So it'll work for that homework. Later, when they've upgraded ggmap to work properly and fixed any outlying bugs in ggplot 2.2.1, they'll all work together. That's just not the case right now. These things happen. These things do not happen, however, if the packages are all developed by the same people, because then they tend to fix everything simultaneously. So, for instance, the the SF package, the new spatial package, would not have any of these problems because the authors and co-authors on that are the same people who are in ggplot, that being Hadley, Wickham, and like his associates. So the stuff that if you use the SF functions for this, it would all work. The thing is the homework isn't built around SF because I'm new to SF and I couldn't like restructure the homework. When I teach this in the spring, hopefully I'll rebuild it around SF, which is very new to me. So, anyway, anyone have any questions before I get started? Cool beans. Okay, so today's lecture is going to be on using R to work with social media and to work with text data in terms of text mining. So things like doing actual analysis and preparation for analysis with text data, which a lot of the data you're going to get from social media is going to be text data. Some of it's going to be social network data. I'll talk a little bit about that, but that's kind of outside the scope of this class. So, what we're going to cover today, we're going to begin with talking about terminology. So when you're working with social media data and with text mining, there's very specific terminology associated with these things and associated with the greater use of sort of communication technologies and software, stuff that you need to know to figure out what it's talking about when you do stuff in these packages. And also text mining has its own very particular lingo that you need to know, otherwise none of the functions will make any sense and you'll have no idea what the hell you're doing. So, talk about that. Then we're going to transition into actually collecting Twitter data and doing a little bit of analysis with it using the social media social media lab and streamer packages. Then we're going to go do actual text mining with the TM package, and I'm also going to talk a little bit about some other packages for doing text mining. All this stuff, social media stuff, text mining stuff, is kind of the cutting edge of a lot of social science, because the internet is sort of this constantly changing thing that's been growing in importance for people's analysis. So these things tend to develop quite rapidly. Social Media Lab is a brand new package that works really well, and it's sort of the way ideally all packages should be. But things for less popular stuff tend to be complex, idiosyncratic and stuff. You could learn a lot of coding by trying to navigate some of these more complex packages and stuff, because often with like social networks and stuff, it's just like one guy figuring out a way to build an R package to negotiate this kind of stuff. And it's only after something really gets people's attention, people get excited about it, do you get actual groups of people getting together to write an R package that's really nice for handling this stuff. So it's constantly developing. Every year you might be moving on to another package, but the underlying logic and the terminology and stuff will basically always remain the same. So that tends to be more important than the specific packages. Yeah. So we're going to start by talking about collecting Twitter data. And to do that, I think I've got some terminology first. Yeah. Terminology. So, the first thing I want you guys to know, and that you're going to hear a little bit of and a lot of if you continue to do anything with social media stuff and also sort of generally interfacing with any kind of online stuff, is the term API, which stands for Application Program Interface or Application Programming Interface. So what the API is it is can be thought of as an interface that exists as a way of allowing a computer to communicate with something else. And that something else could be something like a website, web applications, another piece of software, or something like that. They will usually communicate over some sort of standardized protocol, some sort of language they use to talk to each other. But the API is what sits between your computer, or in our particular case, it sits between R and something like Twitter, or between R and Facebook. Or, from last week, it's what sits between R and the US Census database. What we used in Tidy Census before was we gave it an API key that we got by requesting it from the Census Bureau. You put that information in, it feeds it to the API, authenticates you, and then your computer, which is using R, talks to their database servers through this application programming interface. And with web type stuff, that being Twitter, Facebook, all that kind of stuff. Typically, this communication is done via Hypertext Transfer Protocol, HTTP. Every time you open your browser and open a website, it usually says HTTP://. That's because your browser speaks in Hypertext Transfer Protocol. It's sort of the universal protocol for handling textual, like internet-type data. But it's also usually what's used for communication over APIs with most websites and things like that. So that actually also means if you take an API call that is produced by R or something like that and you put it in your browser, it will return what R would see by doing it. You could copy and paste it straight into the browser, send those tokens. You'll get back a file not formatted for humans to read, but formatted for computers to read. So, yeah. R packages interface with websites and databases virtually always go through an API. If you don't go through an API, it's something else called scraping, which I'll talk about in a minute. So APIs make accessing data for you very easy, but they also allow websites to limit or control your access to their resources. So this is very useful to them because they don't want people doing things like requesting gigabytes upon gigabytes of data continuously. If you're going through an API, it means you have some sort of key that uniquely identifies you as you, and if they don't know who people are, they can deny them access because it requires you identified. That means they can do things like limit how much data you get from them. Websites really don't like people pulling huge amounts of data. Twitter doesn't want people to scrape their entire database of every tweet that's ever been produced, for instance. APIs allow them to very selectively limit what you can see and what you can get. And in an age of sort of people posting everything on social media, there's privacy concerns that make them not want you to be able to just grab everybody's stuff. APIs limit your access, but also make your life easier. Okay. XML and JSON are two file formats that are commonly used for communicating via an API. So often when you make some sort of request from your computer to something like Twitter or Facebook, what it will send back to your computer is going to be data in a very specific structured format. XML, I believe, is extensible markup language. It's sort of a more extended version of HTML that allows you to add all sorts of new and different things to it. It's a markup language. There's also JSON. I forget what JSON stands for, but it's sort of a plain language looking structured language for providing data. Basically, anytime you query something from a website, it's almost always being returned to your computer as something in XML or JSON through an API or something like that. When you open a web page and it displays a web page in your browser, that's usually coming as some sort of formatted HTML page or something like that, but behind the scenes it's often XML or something, creating something and then producing an HTML page. So these types of files, XML and JSON, can be parsed in R into things like data frames and lists using the packages XML and JSON Lite. So R packages exist for translating this information for you, so you don't have to manually do it. Because otherwise you basically have to learn XML or learn JSON to parse this stuff. You don't, somebody else has already done. Then one of the last things that's got to talk about is scraping. So today we're going to be doing basically everything through APIs, but if you want to get data from some particular website or something like that that doesn't have an API, a good example is Craigslist. Craigslist does not have a public API to let you get data from it, which is annoying if you want to do something like, say, I did a rental housing market study during my master's program many years ago. But we needed Craigslist, because Craigslist is one of those places that people are most likely to find information on rentals. Well, Craigslist doesn't let people scrape it because it's an advantage to them. They can sort of like keep all this data to themselves and do whatever they want with it, which means they can sell it to other people. Sometimes no API exists because they want to market the data themselves. So because of this, we ended up writing one of my collaborators wrote a pretty big Python script that automated the process of scraping every rental listing off of Craigslist in this particular area continuously, every day, multiple times per day, scraping these things down. Well, after doing this for a week or two, he found that he was getting denied requests. And so, being the reasonable and ethical person that he was, he did it on a different computer. And he did it until they stopped. And then he was like, oh, well, I know what the reasonable thing to do is. Let's have it swap IP addresses continuously and run on multiple computers. And did this on the university network. We got the university blocked by Craigslist by continually scraping these things. And that's because Craigslist is like, why the hell are we getting essentially denial of service attack from an American university? Well, the answer is we were doing a housing rental study and we were querying them way more than we should have because we didn't know what we were doing. But we got a lot of great data for a whole summer. It took them a while to shut us down. Anyway, they eventually wrote a cease and desist letter to him because they managed to figure out who was doing it. And of course, we cease and desist, but we'd already gotten a full summer's worth of data, and so we could still conduct our study. And yeah, so that's scraping. There's no API, so we kind of came up with our own way. One of the reasons sometimes a company will produce an API is so people do not do that, right? Because it drives them insane. Because the API can do rate limits, so it can make it come in at a reasonable time, and they can control what information you get. With the Craigslist postings, we could get everything. Everything that they could possibly display on the website we could pull down, which is great. Sometimes Twitter kind of gives you everything. Facebook limits you a lot what you can get. Instagram limits you a lot what you can get. YouTube doesn't have anything of value anyway, so they let you have everything. Yeah, but sometimes you gotta scrape stuff. Scraping is really about doing things like you're essentially opening a browser in the background, say in R, pulling all the text from it, and then using text processing, kind of stuff we learned in week 8 and also some stuff from today, to pull out the useful information that's in the raw HTML. When you right-click on a web page and get view source, your computer, like R, can just parse through that text and grab whatever you need out of it. It's common with people doing stuff with like pulling down movie data from IMDb. You can just scrape every page from everything you want, automate the process of opening new browser windows, basically, grabbing all the data, putting it together and making a database. And there's packages that exist in R and Python and things like that that will sort of automate and make it easier for you to scrape stuff from places. I don't cover it today, but it's out there. If something's visible to your browser online, you can get it into R. Just a matter of figuring out how to do it. Sometimes it's not that difficult. So yeah, to be clear, if you're using an API, you're not scraping. So I'm not going to be talking about too much today, but know that this exists and know that that's the term for it. Never know when you're going to want to do it. Yeah, it does require more technical knowledge than an API. Sometimes APIs are even quite convoluted. And APIs also change all the time. Facebook updates its API more regularly than I wish they would, and every time it breaks every package associated with it and drives everyone completely insane. They do it all the time. But the nice thing is, at least it's documented. Scraping, there is no documentation. You're off in the wild on your own. And then lastly, I mentioned this a couple times, the rate limit is what a web page, a service, or something uses as a way to control how much data you can get from them. Basically, something like Twitter usually limits you to downloading a certain number of tweets per minute or something like that, just so you're not just ripping huge amounts of data down from them. If you want to automate like an R script so that it pulls down like, okay, I want to pull down like 10,000 tweets per hour and I want to space them out. So let's say if the rate limit was you're allowed to download 1,000 tweets every 5 minutes, what you could do is you could write a script that says download 1,000 tweets, sys-sleep 5 minutes, and your computer will sit there and do nothing for 5 minutes, like the R console, and then run it again. Often, what you'll do is you'll find your rate limit on Twitter. Let's say you want a lot of tweets, like you want a lot of tweets. You'll have some computer, like one of the CSD servers or something like this. I have many people I know do this. They'll be like, okay, you set my grab tweets to my rate limit, time it with sys-sleep, and then leave it running for 6 months. And it will just grab and grab and grab. Twitter's perfectly fine with this because you're exactly abiding by their rules. You run it back. You come back in 6 months, you've got 500 million tweets, right? You've got a database to work with. That's how you do that. But sometimes it just takes time. The fact that it takes time means there's a cost to it, and that keeps a lot of people from doing very, very large work. But keep in mind, it's just time, and if it's automated in the background, you have to wait, but there's no opportunity cost because you're not burning your actual time on it. Automate stuff and do it behind the scenes. Okay, so the actual social media analysis stuff we're going to do today is going to be primarily based on Twitter because Twitter's pretty easy to work with, and it's also, everything we learn from Twitter is generalizable to other networks. Twitter's also the most public of the social networks as far as basically almost anybody who's tweeting, you can see their stuff, whereas Facebook is very locked down, Instagram even more so, and like I said, nobody cares about YouTube, so whatever. Okay, so Twitter has two different APIs that you can get data from, and they're quite different. The first one is Twitter's REST API. The REST API allows for both reading and writing Twitter data. So you can get tweets through the REST API. You could also post tweets. So you'll often see tweets from organizations, things like that are sort of automated postings. You can make ours send tweets. You could do it to do status reports to people and things like that. There's some Twitter feeds that are nothing but a way of broadly communicating to a large number of subscribers some sort of regular information. So this API, it goes either way. It's also another reason, do not give people your Twitter credentials, because if they have Twitter credentials and they use it like an API, they can read everything you can read, but they can also write to your account. So the reason, like in my files for today, my credentials are not in there because I do not want people tweeting as me on my Twitter feed. Okay, not that I use Twitter and I'd like to keep it that way. Okay, so the REST API allows you to obtain tweets from specific dates and places pretty easily, but it doesn't give you everything. It gives you samples, right? So you can get little snapshots of time and space, but it's limited in that it will sample like a maximum of something like 1% of them. For a very dense area, 1% of tweets could be a lot. For a very small area, it could be very little, and it also limits the size. You can't do things like, let's say that you're really creepy and you're stalking one particular person, you want to get all of their tweets, you can't focus it directly on their house geographically and grab them. There's a maximum and there's like a minimum size you can do. And nice thing is, though, it's still pretty small. So I did a project where I grabbed tweets very specifically from different neighborhoods in Seattle to look at like the spatial differences and sentiments across different neighborhoods in Seattle. You can do stuff like that at a pretty fine grain. You just can't go down to be like really stalkery down to low levels. Date-wise, I think you can also go back pretty far and stuff, and the window can actually, I think you can do individual days with it, but I'm not 100% sure. I mostly work with space and not time. So this is really good for obtaining lots of data, data over time, data in particular spaces. So we're mostly going to work with the REST API. The second API is very different. This is the Twitter Streaming API. The Twitter Streaming API obtains tweets live as they are being posted. It is like a live faucet of whatever is presently being sent to Twitter. It just is also then sent to you. So it only gives you tweets that were posted while you're watching it. So while the connection is open, it's downloading tweets. But it's like a faucet. It's basically giving you everything, more or less, almost everything. This is really good for following trends as they're happening and live events. So if you know something is coming up that you want to do some sort of analysis as, you can prep your like streaming API poll and run it while it's going on to see this live thing. People very commonly do this for elections. That's how news agencies start to get those live tweet things coming on the news. It's the streaming API. They're just pulling it straight down and they're doing the same kind of analysis we'll be doing today with streaming. It's neat. It's also neat to do things like do a 24-hour stream, like exactly 24 hours, and watch as tweeting goes across the world, wrapping over the globe, because you can see when people are waking up and going to sleep, because the tweets will fly across the world. Super cool, right? And there's reasons you can come up with to do that. It's neat, but it's different, and you access them in different ways. So, here's some setup. So if you want to work with Twitter data, you're going to have your own Twitter account, and you're going to have to set up an application in Twitter to do it. This tutorial's online. I think I've got a link on the website. I'm not having the expectation anybody's done that today or anything like that, but you need to do it yourself, and it can be a little convoluted, and they change it all the time. So I've taught workshops at conferences like the Population Association of America and stuff doing this like Twitter stuff I do today. The thing that takes the longest for the entire workshop is just getting people set up on that damn Twitter application, even though I say in an email repeatedly for the weeks lead up to the conference to have this set up before you show up in the room. It's still a pain in the ass, and lots of people come and are like, I have no idea how to get it working. So I have no expectation I'll have it set up now, but I've got pretty good instructions on it. Anyway, so the packages we'll be working with are Social Media Lab mainly. I've got Tidyverse loaded here, Stringer for working with strings. I forget why I loaded Grid. Grid is the underlying graphic system that ggplot uses. grid graphics replaces base graphics. Streamer for getting the streaming API. ROAuth is an authentication package for R that lets it do sort of exchange credentials using API keys with a lot of different things, Twitter included, but it also works with Facebook, Instagram, all that kind of stuff. And then I've got the TwitR package here, Twitter package, and I don't actually know if I'm calling anything in that except stuff that's going into Streamer, but it's up there. So what I've done here in the setup is normally for Twitter, you have 4 different keys associated with your Twitter account. You have an API key, an API secret, an access token, and an access token secret. You need all 4 of these things to do like full-blown Twitter stuff. Do not give people your API secret or your access token secret. Those are essentially like your passwords, while your API key and your access token are kind of like usernames for API stuff behind the scenes. Preferably, don't give people any of this stuff. If you share scripts with people, keep all of your Twitter information in a separate file that you do not give people, that instead they can plug in their own Twitter credentials in these things. And you'll see if you download the lecture files for today, you'll see exactly how I set that up and did it. I used a file I call like twitcred, and I just load that separately and then pull each of these like API things out of it by doing like twitcred $, whatever object it is. So don't share that stuff with people, otherwise they can post on your Facebook or they can post on your Twitter and stuff like that, because APIs are bidirectional. Okay. I also have to set some URLs to tell OAuth. You see here, ROAuth was the package. Twitter, at its own website, uses OAuth for its authentication, even with your browser and stuff like that. So you basically what you're saying is you're telling this Social Media Lab package and the Streamer package that these are the URLs to send information and receive information from, as if you were just giving a browser URL to them. It's all using HTTP and communicating the same way your browser does. It's just happening behind the scenes inside these packages. Okay, so with that set up, the first package we're going to talk about today, second my camera's out of focus. There you go. Okay. So, first package we're going to talk about is Social Media Lab, which is a relatively new package that, for me, has basically completely replaced every one of the old social media packages I used to work with, that being our Facebook, Twitter, Instagrammer, all that kind of stuff. Not that I do Instagram stuff, but my friend Keelan does Instagram stuff. So, Social Media Lab is what I would call a one-stop shop for accessing social media data and transforming it for network analysis or textual analysis. The neat thing with Social Media Lab is it works with lots of stuff. It works with Twitter, it works with its REST API. At the moment it does not work with its Stream API, but I wouldn't be surprised if that changes at some point. It works with Facebook to access pages and public posts. Facebook is unique versus like something like Twitter in that on Facebook, like when you browse around on Facebook, most people you can't see their page or can't see post summary, you see very limited ones. Whatever API you have connected to your Facebook is connected to your Facebook account, so your computer, your R, can only see what you personally would be able to see by loading the web pages on Facebook. So if you want to look at individual people, you're only going to be able to see information of the people who are friends of yours or who have stuff that's public. The thing is, Facebook, most pages are completely public and you can see like public posts. So the most useful thing for working with Facebook and Social Media Lab and Facebook in general and R is using public pages. I like to do them for things like the pages of major politicians. The Trump page was a gold mine during the election for doing social media stuff. So my old tutorials on Facebook were all about pulling down stuff from the Trump page to see how all of those things were clustered in very suspicious clusters that might be geographically centered in Eastern Europe. So very fun and interesting. A lot of people have done a lot of work using public pages. And in Twitter, also politicians, because some politicians tweet a lot. Instagram is another one you can do with Social Media Lab. You can get public pictures and comments from Instagram. The problem with Instagram, however, is it's really hard to get API access to Instagram. It used to be cake. Now you basically have to jump through a lot of hoops for them to allow you to set up an application to get API access. It's a huge pain in the ass. I do know somebody who did that and did a bunch of work using Instagram for health studies, but It's hard now, but I don't know many people who want to do Instagram stuff, but it's a huge pain in the ass.
I know this is off topic, but how do you use Instagram for health studies? What do you do?
I'm glad you asked. So the way he did it was, so this is my friend Kevin, for people who don't know. In his dissertation, he was interested in looking at people's health behaviors through like the stuff they're signaling on their social media, and that the language they're using around health stuff and food and exercise and things like that. Well, the thing is people do a lot of posting pictures of food on Instagram and exercise stuff on Instagram. So it was really neat. I don't remember, you'd have to ask him specifically about it, but he got API access, he set up an Instagram application, scraped a ton of Instagram data, and then did lots of text mining stuff, kind of stuff we're going to be doing today with this Instagram stuff. Super neat. And this is like health studies, and he was looking at racial differences in these things, and like stuff, it panned out. I mean, it was a great dissertation chapter. This stuff is super like wide open. Social media stuff is very fresh in the social sciences, so there's a million cool research things you can get into with this kind of stuff. And you might think that's like, well, it's neat, but most of the stuff isn't representative data. Emilio Zagani up in our department has written multiple papers on how to make these biased data you get from things like Twitter, Facebook, and Instagram into representative data that you can do for things like researching like migration, demography, actual like serious topics. You can calibrate these measures to do it, and sometimes it's not actually that complex. Super cutting edge, and UW is one of the leading places in the entire world for this kind of work right now. So you're in a good spot for it. A lot of grants, a lot of money for this stuff right now too. You get into it, you get good at it, you can go places. Then Social Media Lab also does YouTube. It will do videos, comments on videos, user kind of information. If you've ever read YouTube comments, maybe you'll know how useful this might be, but I never know. I still haven't seen anybody do anything useful with YouTube analysis, but I'm sure somebody's going to figure out how to like do serious research on rampant shit posting, but we'll see. Okay, and then the neat thing is data from all four of these networks can be collected and analyzed using the exact same functions and the exact same syntax. You don't have to change anything to work with any of these four social networks. Social Media Lab does it all with the same just handful of functions. There's a link here. It says see this introduction to see exactly how much you can do. This leads to a big vignette and like a tutorial on how to do all kinds of crazy stuff with Social Media Lab. It's a huge package that does a lot. I love it. Only going to cover Twitter today. Facebook, YouTube are really similar to Twitter. Instagram, like I said, it's possible in theory to do it, but it's gotten much harder to do it. Okay, so the Social Media Lab workflow. It has a really simple workflow for collecting data to feed into your analyses. You start with the authenticate function to give your credentials to Twitter or Facebook or something like that. You will pipe your authentication to the collect function, where you will specify search parameters for things you want to get, like terms in a tweet, locations, time, date, that kind of thing. Then, from collect, you pipe it into either something for text analysis, or you could save it, or you pipe it into the create function in Social Media Lab to generate network data. So, using just these 2 or 3 functions, it will do all the searching and process the data into tidy-ish data frames for use in whatever you want. You don't have to handle JSON files or XML files behind the scenes. In fact, you'll never even know they exist because it totally handles everything for you. This is awesome. This is actually kind of life-changing for people who do any significant social media network stuff. It's pretty amazing. It won't necessarily do completely everything, but everything I've wanted to do, I've been able to do in Social Media Lab with like 2 lines of code when it used to be dozens or 100 lines of code. Seriously, all my social media stuff is like 2 lines of code, and that's only because I'm breaking it up to fit nicely on a slide. Like, it could be 1 line. It's crazy. Okay. So, let's start working with a REST API in Twitter. So, what I've done here is, this is something I did back in, I think I did this in last May, but I kept it because I like the tweets and some of the subject matter. Anyway, so Here I'm creating this tweets Trump. I wanted to get a bunch of tweets that just contained the search term Trump. So not necessarily from Donald Trump, but people talking about Trump or things that are coming out. So all I had to do was say authenticate, so Social Media Labs authenticate function. I'm saying authenticate with Twitter. I give it my API key, API secret, access token secret. Each of these is just a single character string that are my API keys or whatever. That's the entire function. It handles all the authentication, talking to Twitter, getting me set up, ready to download data. So authenticate, I then pipe this to collect. I say collect, search term, Trump. I want Trump. Language, English. Verbose equals true. Verbose will return in the console. I believe it shows me the status of it downloading tweets as it's going. If you're downloading a lot of tweets, you probably want status updates as it goes because it might take a while. Some of the stuff is time consuming. Pretty sure that's what verbose does in this case. And then I just pipe it into as Tibble to convert it into a data frame so that I could display it here. So this is what I got. Tweets Trump, I'm arranging them by the number of retweets. So these are the top things are going to be the ones that were retweeted on Twitter by the most people. So basically shared by the most people. And then I'm just selecting the text that is the body of the tweets. So the most tweeted things were the number one most retweeted tweet was come and see Trump news and see what the Orange Menace has been up to. But there's all kinds of things. These are actual just tweets. So I managed to download 1,500 tweets from Twitter with this search term using just this tiny little bit of code. It's that easy to get Twitter data now. Yeah.
So how long, because in the Twitter, I guess, package, if you tell, like, you download this for like 50 seconds or whatever, right? Like how does that end?
There's an argument you can give to collect. I think it's something like N. I think it defaults to 1,500, but I believe you can give it either a number of tweets or a time, like a time to go.
What about like more popular or more followed people tweeting versus, like, can you do it according to followership?
Oh yeah. You could actually sort. So it gets the tweets, but it also gets information on the users for those tweets and their number of followers. So you could actually also sort this by the number of followers. I forget if I actually have an example of that in here. I may actually have an example of that. I know I do in my old PAA workshop. Yeah, you could sort by the number of followers. You can also pull down tweets from specific people and pages and things like that. So it's pretty flexible. So the answer is, to my understanding, yes. Yeah, pretty neat. So here's another one with REST API. This is me doing it geospatially. So in this case, I wanted tweets that were centered around the University of Washington, so the general kind of U district area. Same thing, my authenticate, it's exactly the same here. You could actually, if you wanted to save this entire authenticate as an object and just pipe that object in instead of authenticate. But I just read authenticate. Then I said collect geocode equals latitude and longitude. So I'm saying I would like to collect tweets around 47.6552083 degrees at negative 122.30833. That is like dead center, I think, on Mary Gates Hall in UW. And in a 2-mile radius of that area. So that's a pretty big area, but it's all around.
Sorry, and in the user info, you also know where they are?
To a degree. So this will get geotagged tweets within an area. If somebody has not geotagged their tweet, it won't show up on geocoded things.
And that is no longer the default, right?
Yeah, I do not believe it's by default geotagged anymore.
It used to be, and now you
Yeah.
have to opt in.
Yeah, you have to opt into geotagging. So, a lot of people are still have geographic information. Luckily, but yeah, it's definitely gone down. And for people who I know who are doing migration research using geotagged tweets, that's kind of an annoyance, but there's still a ton of them. And it just means that's a different calibration you have to do to make your data representative. So you figure out ways to do it. Then what I've done here is I did search term space. So the thing is in the Twitter API, you have to give it a search term. It requires a search term. You can't give it nothing and collect everything. But most tweets contain a space. So this is my hack. I say search for space. That will return every tweet in that geographic area that has a space in it. Most of the time it's going to have a space. Language English, verbose equals true again. Then I've arranged them by retweet count again, and then just pull the text out. So at the time I did it, and this is what I love about this particular thing, it was completely random but come out this way. So I'm into sneakers. I like shoes a lot. This is somebody selling limited edition Air Jordan 3 5 Lab 3s, Air Jordan 4s, Air Jordan 4s. This guy's like hawking high-end sneakers in here. This was the very first pull down I got, and I've kept these. I'm going to keep them. It makes me very happy. These are local tweets in the area. Somebody getting sushi in Wallingford. Pretty neat. Yeah, so they're local. Yeah. So, a lot of things you can do there. If you get information in Social Media Lab, I go through its like tutorial. You could see that you could basically apply those same principles to doing any social network. And there's also all sorts of other arguments and options you can do to be more specific with tweets or whatever like that. There's a lot of options. I recommend looking at the tutorial. I'm going to jump now to looking at the streaming API. So there are multiple packages that can access the Twitter Stream API. The one I am familiar with is StreamR. There might be newer, nicer ones, but I didn't have time to really poke around and see what else is out there. The Stream API, because it's sort of a live feed rather than historical feed, is a little less commonly used in social science. And because it's less commonly used, the packages are a little bit more rough around the edges. They're a little more idiosyncratic in how they work, a little bit more complicated to deal with. And especially their setup is more complicated. It's my belief that more people are going to start taking advantage of the Stream API, and then either Social Media Lab's going to pick it up if they haven't already started, or there'll be some similar tidy package that will handle the streaming API. For now, Streamer's a little finicky, but it works. So, the setup for this is a little bit complicated. There's some weird stuff going on here. So, we begin this with having to download a file from curl.hacks.se. So what this actually is this is downloading a type of certification file needed to do curl certification into OAuth. It's a little complicated. Google if you're interested in what all that means. The gist of it is you need this file that is going to be used to generate like sort of permissions for this streamer API. This just ends up being the best way to do it. You download this file, then we go into that OAuth package and use OAuth factory $new, which is a function inside of OAuth factory, to generate Twitter credentials to be used with the streamer. This is the syntax for that. You just want to copy it exactly and then fill in your API key, API secret, and then those URLs I had way back at the beginning of the lecture. This just tells it how to generate it. This OAuth factory here is a generic function. Anything that uses OAuth type authentication, you would use this basic syntax to generate a key for it. So this is like sort of a non-package specific way of generating credentials for websites. Then you're going to do twitcred $handshake. So inside of the object created for it is actually a function you're going to run. So it's really weird stuff. You're going to give it as a system file this curl SSL file that was generated here. Tell it to use the our curl package for authentication. You're going to run that. Then in your console, it's going to open a prompt that's going to tell you to input a number or copy a number. And you're going to have to insert this number given by a web page it's going to open. It's actually going to pop a browser window open for Twitter with a number. You copy that number, paste it into your R console, and hit return. It's weird and annoying. Normally that stuff would be done behind the scenes, but like I said, rough around the edges. Then what you'll do normally is you will save that twitcred file so you never have to do that again. Because this twitcred will always work. I'm still using the same twitcred that I used for my PAA lecture I gave like a year and a half, 2 years ago. Now, I'm using the same one. Create it once, it works for my account in perpetuity. Yeah. Yeah.
So, can I clarify that social media love doesn't have StreamR,
Mm-hmm.
and then Twitter REST.
The REST API is in Social Media Lab.
Okay.
Yeah, the streaming API is in Streamer, but I wouldn't be surprised if there's a smoother package either out that I'm not familiar with, or something will be added to Social Media Lab to do the streaming API. This is what I'm familiar with, though. I don't do a lot of stuff with Twitter, so I might be a little behind the times. I know Social Media Lab is cutting edge, though. Like I said, the streaming API is less used in social science, and As evidence of that, I don't use it very much myself, so I'm not as familiar as I could be. Might be something new in. Okay, so in Streamer, once you've authenticated and everything like that, the function sample stream will download streaming tweets with no particular topic. In the streaming API, you can just get things with no search term, unlike the REST API. So for example, you might do this. Say, sample stream, blank text, I'll talk about that in a little while, timeout 10, and then you give it OAuth equals those credentials you did. What this is going to do is it's going to run for 10 seconds and just grab all the tweets coming from the streaming API. So the streaming API is like a perpetual, like fully automatic shotgun of tweets flying out of Twitter to you. It just grabs everything. You just basically, it's like putting out a bucket into the rain and catching everything. The time is how long you hold that bucket up for. You pull it back, we get a bunch of stuff. There's also a filter stream function that will download streaming tweets based on some kind of search parameter. So it's still streaming tweets that are coming out, but instead you're putting out like a very specific net that's only grabbing some things that are popping out. In this case, I did tweets Trump here, filter stream. Now I'm doing track equals Trump. So it's looking for, it's only going to grab tweets that are being posted right now that have the word Trump in them. I'm not 100% sure if it's case sensitive or not. I would wager it probably is case sensitive, so keep that in mind. Again, I ran it for 10 seconds and gave it my Twitter credentials. So the first argument in both of these functions is a file location to write the tweets to. If you leave it blank like that, it will write the tweets to the console. But the same thing as write to the console would be assigning them to an object. So I've done it here because I want to assign these tweets to an object in R rather than to save them as a local file. If you're going to be grabbing lots of tweets all the time, you probably want to save them as files directly on the computer rather than as an object in R, especially in a loop. Every iteration of the loop, it would write a new file. So you can just continuously do it. If you accidentally shut off your computer, you didn't just lose the objects loaded in R's memory. Instead, it would just be file, 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 file. I know people who have a script that when their computer starts up, it starts grabbing the stream, and the entire time their computer is on, the script is running in the background grabbing them. Anytime they turn their computer on, it's grabbing the stream. That way, using their computer for a year, they have an entire year's worth of streamed tweets. It's just perpetually being collected because they never know when an event they want to track is going to happen. So they're just grabbing everything. Never know. They just have it constantly rate limited. Twitter doesn't care. They're cool with that. Okay. So, once you've streamed your data in using these streamer functions, you are going to need to parse them from their native JSON format into some sort of data frame for them to be useful. Social Media Lab does this without you even knowing it. It just does it. Streamer does not do this for you. Luckily, there's functions to help you do this. So, I've grabbed that tweet stream object that I just created right here, tweet stream. What I'm going to do is I'm going to put it into a function called parse tweets. So I believe this is in the twitr package, the Twitter package. I'm saying parse tweets, tweet stream, verbose equals false. I'm hiding additional information it would normally give. I forget exactly what it is. Verbose is a common argument in functions that work with like big data stuff that might take time. I just do parse tweets. Parse tweets will take those JSON files and convert them into a list for you. And I saved it as tweets from stream. Then I'm going to make it into a tibble, so it's going to turn it from whatever that format it is right here. I forget if it's a list or a ugly data frame. I'm going to organize it as a tibble being a data frame. I'm going to arrange it by the number of followers. So in this case, rather than arrange it by the number of retweets for the tweet, it is by the number of followers, like you were saying before. And then I'm going to select only the names of the people. So I got tweets from these people, and these are the people in order of the most followed people in this particular one. This is fun because this reveals a common issue you'll encounter when you look at the names of people or the text in tweets. There's Helen Howell, there's somebody who just has whatever that is, and then this. This right here is a long string of Unicode characters. This is somebody who, judging by the range of those Unicode characters, I would say that that may be Korean text, okay? So you'd have to parse this into like a Unicode reader, copy paste it, and render those Unicode characters to see what this actually is. So this is Unicode extended, like UTF, I don't know if this is UTF 16, UTF 8 characters, whatever. You may have to parse that differently. Some functions in R, if they receive these, will give you errors. So know that sometimes you're going to have to remove things that are all like these Unicode characters, and it's incredibly common to encounter these in social media data because people speak and use many different languages on social media. Be aware of this, and you have to figure out your own solutions for how to deal with it.
It's Japanese.
It's Japanese. Okay. Yeah. Yeah. I knew it was one of them because the numbers are so high that the higher up Unicodes are Japanese, Japanese, Chinese, Korean, and further as you get up in that range. Yeah. And then other stuff. So given the time, I'm seeing that there's a lot of it's like a fair amount of Latin American stuff. I wonder what the time of day. It must have been during U.S. time. But anyway, fun, right? So this is off doing it by followers. So when you're actually using Streamer, keep in mind that the streaming API collects tweets in real time. So it's most useful when you leave it running, as I've said before, for a really long time. You can use it to monitor events as they're happening or capture snapshots in time. One thing I did here is I let it run for 1,200 seconds to replicate an example by Pablo Barbera, who is the author of the package, just to see tweets as they're sort of live tweeted in the United States, and then to map them, because I want to see it's like where are tweets coming out in essentially what is the density of tweets within this given 1,200 second period. So the syntax for this is a little bit big, but it's not stuff that it should not be unfamiliar to you guys. What I did here is I said filter stream. I'm going to save this to the file tweetsus.json. So remember, filter stream is outputting by default JSON files, so you want to save them as .json if you're going to save them locally. Locations. This is a bounding box, like we saw in the geospatial lecture I gave. This is a bounding box that approximates the United States as a square. You're going to get some of Canada, you're going to get some of Mexico, you're going to get some of the Caribbean, that kind of thing, but it's approximately a square. Timeout 1200, so run for 1200 seconds. Use my Twitter credentials. I let that run. Went up, made a cup of coffee or something like that. Went for a little while. Came back, and now I have this tweetsus.json file. I do parse tweets, that file name, so it's grabbing the file actually off of my working directory where it was saved. It's going to parse those tweets into a data frame. Then I use the function mapData_state to get a map of US states. It's just the function to produce that. Then I made a data frame where X was as numeric, because by default the tweet data comes in as character, I believe. As numeric, tweets.df longitude, and as numeric tweets.df latitude. Latitude is going to correspond to Y coordinates up and down on my map. Longitude is going to correspond to my X coordinates, left and right. Then I had to refilter. For some reason I had, even though I said 25 is my minimum latitude, I still got some tweets below the 25th parallel. I really have no idea why. I filtered those. Then some ggplot syntax. I say, first, ggplot map.data. Map.data is that state map I got. So this is kind of like what we did with ggmap and stuff like that. That's the basis. Then geommap, map ID equals region. This is going to create a map of the United States where my stuff that it's grouped on to draw my lines is my region, US. Map equals map data. Fill white, color gray 20 is going to draw gray lines between all the states of size 0.25. I did this thing, expand limits is going to create a little bit of a buffer around the map. So rather than being exactly the limits of the data, I widened it a little bit for to make it look nicer. Then all these theme calls are just getting rid of crap I don't want on the plot. Lots of vertical and horizontal lines, backgrounds, axes, all that stuff I don't care about. We know what the United States looks like in a map. I don't need any kind of other indicators on there. Then I tweaked my margins a little bit. And then geom point, data equals points. Points are just the tweets, just their x and y coordinates. I need no other information from those tweets. I'm just going to plot their coordinates. AES, x equals x, y equals y. Size 1, make alpha, I did this 1 divided by 5, 20%, so 80% transparent, 20% visible. Color, dark blue. So what this should produce is a map of the entire United States with partially transparent dots where each dot corresponds to one tweet downloaded during this 1200 second period. This is what it looks like. Every single dot or cluster of dots is tweets. The darker it is, the denser it is, there are more tweets located in those locations from people who had geotagged tweets in this 1200 second period. So you can see, because my bounding box was approximately United States square, I'm still getting tweets in the northern part of Mexico, tweets in the southern part of Canada, and actually, one of the fun things is that the majority of Canada's population lives south of Seattle, so the actual majority of Canada's population is in this general area over here. So I'm getting a lot of Canadian tweets. But yeah, you can see the density of all the major cities in the United States, right? Pretty cool. So I've essentially plotted the internet-connected civilization in the United States using 1,200 seconds of tweets. Pretty neat. If you ran this for a lot longer, get denser and denser, you could run it for the whole world, and then you could do things like filter it by time. You can even create an animation, like I mentioned before, where it's going the entire world to spread out, and then you do like hour by hour and watch it flow across the planet based on the rotation of the Earth. Neat. Live data. Normally, we're not as connected immediately to our data as we are like in social sciences compared to like the social media stuff. We're just live. We're tapped right into it. This is super neat. Okay. So, if you actually want to use Twitter data, we're going to talk about text mining. So, nowadays with Social Media Lab and stuff, it's pretty easy to get your social media data, but once you have it, the question is usually, okay, I have 10 gigabytes of tweets. What the hell do I do with 10 gigabytes of tweets, right? That's the much more challenging thing nowadays. There's two different ways people typically use social media data. The first way is text mining, which is going to be the rest of today, or network analysis. We have a class in CSSS 567, Analysis of Social Network Data, that covers methods for approaching network data. Network data isn't limited to like online network data, but it's actually just like networks of people and things like that, but it does have the techniques for handling social media network in a statistical and mathematical way. But it's too complex, I'm not going to do it. But as an example, here is a plot, a network plot of the Star Wars Facebook page, actually, showing every individual person who posted and all the people who liked or shared all of the different posts. So every one of these lines is a connection between different people who liked or shared things on the Star Wars page in, I believe this is only in a day or something like that. This is a big social media graph. That's a lot of data. That's really cool, right? Network stuff is neat. Makes lots of pretty pictures. Anyway, I invite you to get into social network analysis if you want to find out more about this stuff, but I can't cover it. But it's out there. Okay. So, analyzing Twitter text data, it's hard to make sense of very large volumes of data. So they're most useful when you do something like formal text analysis techniques, like parsing text and stuff like that. But keep in mind that sometimes tweets and things can be completely devoid of any useful content, and you'll never be able to make sense of some things. So yeah. What was great is when I was doing my live downloads of Twitter data to make this lecture in the spring, this tweet was captured by my live stream. I just happened to be running it at exactly the right time to capture the classic Kafifi tweet. I was so happy. Okay, now let's get into text mining. So, a little bit of a direction change here. So, what is text mining? So text mining is a term referring to specific types of text analytics that are statistical, mathematical, and computational. So they're processes for extracting information from text which is specifically intended to be read by humans rather than computers. So this is the things we call natural language processing. Text mining is part of natural language processing, which is a huge thing on campus. Text mining can cover things like categorizing the subjects that people are talking about or like authors are talking about. It can do things like sentiment analysis, where you're trying to capture the emotions associated with the language being used, and also things like automated summarization. So sometimes people want to have bots running that will do things like summarize articles into a few sentences. This is all stuff that's part of text mining. So basically, find out what is the most important, or sort of either the key ideas or the key underlying emotions and things behind it, text intended for humans to read. Normally, we want to take in very large amounts of text. If we're people who work with text data, we usually want to work with a lot of it. And if you want to do that, you probably want to produce useful numerical and textual summaries of your data, because it's really impossible to look at thousands and thousands of pages of text all at once. Text is great for reading and conveying information, but computers aren't great at dealing with it, and people are not good at dealing with lots of it at once. So, text mining is really commonly done with social media data, because we typically have a huge amount of it and no idea what to do with it. So, some terminology here. So, TM is an R package for performing text mining. There's another major package, which I think is kind of overtaking it, which is the tidy text package and stuff associated with it. I'm going to talk about that a little later in this lecture. At the moment, I'm more familiar with TM, so I'll talk about it, and I don't know if tidy text, actually I think just as of a couple months ago, tidy text is fully released, so it's very new. Maybe in the spring I'll be teaching tidy text, we'll see. So, basic terminology you need to know for doing text mining. There is a term. Term is a single word in a text, referred to as a term. So a single unique word is a term. Terms can obviously be repeated many times in a text or occur only once, but it's a single word. A document is a collection of terms. So a document could be something like an email or an entire book. Sometimes a document could be one page of a book, depending on how you want to think about it. A corpus is a collection of documents. Multiple corpus are corpora. So a corpus would be something like a database filled with emails, right? That'd be a corpus of emails. Then a dictionary is a set of relevant terms to some particular thing you're interested in. So they could be terms like you could have a sentiment dictionary where you have a dictionary of positive words and a dictionary of negative words, or you could have words that are associated with a particular topic you want to use for categorizing things. Okay, so here's an example corpus that's created just by some tweets I got from the University of Washington. So what we've done here is you can manually create a basic corpus by taking a vector of character data and running this command vector source on it to read it in, and then vcorpus to corpusify it, to turn it into a corpus. So what I did here is I loaded the text mining library, I created UW tweets, which is just 4 UW tweets. Then I took this vector of them and I said vector source UW tweets, then vcorpus that, and saved it as this toy corpus. So this is a way to prep it for text mining. So once it's been prepped into a corpus, you can access individual components of it to do things with it. So if I do toy corpus 3, this is going to give me the third element of this corpus, which is the third tweet in it. It's going to say it is a plain text document. So it doesn't know it's specifically a tweet, it just knows it's a plain text. It has 7 elements of metadata containing 95 characters. If I look back on the third tweet, 1, 2, 3, I'm not entirely sure what the 7 elements of metadata are, but they're there. I'm not super familiar with this because I don't do my own text mining, but I know this is how people do it. So I've displayed it. If you do as character, this same thing here, it will just display that particular document in here. Okay. So most of the time, we'll probably be making corpora from sources like a whole bunch of tweets from Twitter or by reading in data from text files. So what we're going to do here, or what I've done here, is I took a sample of emails from the Enron corpus, which were emails, internal emails at the company Enron sent around before the company collapsed in a giant pile of fraud and embezzlement. These tweets, or these not tweets, but these emails were assembled by UC Berkeley students. You can download a zip file of it. Here, I did this. I downloaded the file directly from my GitHub. I unzipped it into a directory here, basically into a subdirectory from the folder I'm working in, and I just take a peek at it. So I get a list files here like we did weeks ago. I see that there's 100 individual files in this particular folder. Each email is its own file, right, in this particular like zipped up thing. Okay, so I'm gonna read these in. What I say here is, well, what I want to do is I want to make a corpus where every document in that corpus is a single email in this Enron sample. So what I do is I have directory source, which I was going to say, I'm going to specify a directory that contains documents I want loaded in, and it's going to give everything in that directory and turn them into documents. So directory equals these Enron emails, Enron sample emails, mode text. That will pull in every text file in that directory, which I then put into the V corpus that I used sort of at the beginning of this section to create Enron corpus. If I do as character Enron corpus 3, I get this. That's the header of an email, and coming down to the beginning of the email. It just prints it out. It's raw text. It's this single entry, the third element, it's an entire email. And it's got everything. It's got like the whole SMTP header for the email. SMT is the simple mail transfer protocol. It's what emails are sent using. Yeah. Wow, we've got emails loaded in. And they have a lot of stuff. So you could mine something like, you could be mining the data down here. Let's say you had a huge database of other types of emails or other types of documents. You might be searching for things like the actual like people's email addresses. You might be interested in if there is location data. You might be interested in location data. Or you could do things like create a network map of all the people who are like CC'd on emails and things like that. You can pull anything you want out of here if you know how to do a little bit of text processing. Okay, so to do actual analysis on these data, we need to do some transformations to this stuff to make it sort of machine readable. Right now, it's going to be hard for a machine to know what to do with this stuff because it doesn't know that something like x-2 is useless compared to something like this person's name if you want the name, or text down here like impressed that you know, so on and so forth. We're probably interested in these words that maybe sentiments are associated with, and not so much the technical stuff up here. So we have to do a lot of preparation to that. So in text mining, doing transformations to your text are sometimes referred to as mapping your text. So to prepare this particular text, what we want to do is a lot of stuff. First, going to change all the text to lowercase so we don't have to worry about case sensitivity. Next, we want to remove a whole bunch of stuff. First thing you're going to do is we're going to remove stop words. In text mining, stop words are what you call words that contain no useful information. These are words that connect stuff in a useless way. Sometimes it'll be like words like and to, things like that, that don't convey any kind of sentiment or anything, but are necessary parts of human language, but they're not useful to us. So sometimes you'll have to use a database of stop words. I use ones built into TM. Sometimes there's stop words that are specific to different domains of language and things. You can get databases of them. I want to get rid of header terms. I want to get rid of all that junk at the top of the email that's basically telling them how to route the email. I want to get rid of punctuation because we can't do any analysis on punctuation. There's sometimes ways to do analysis, like lumping the punctuation in with the words that precede it if you want to know whether things are questions or not. That's pretty sophisticated, so we're not doing that. We want to get rid of numbers because we don't know how to interpret those numbers. We want to get rid of white spaces. We want to get rid of open spaces. We can't interpret the spaces. We're interested in the actual words, but we want to get rid of them. Then we want to stem the words. Stemming them is taking a particular word and stripping any prefixes and suffixes so that like the word transformation and transform will be reduced to the same word, so that we're looking for basically the meaning rather than the actual like grammatical way it's being used in the sentence. So we stem them. There's functions that will do all of this stuff for us. Okay? Once this is done, maybe then we can actually do some analysis. So the reason we have a package for things like text mining is because we want to automate all that. Doing that kind of stuff manually would be incredible. Even programming functions to do it would be a nightmare. Luckily, other people have done this for us. So this is the syntax I've used to do those operations. Here, I'm creating this new thing called enron strict. So I take my enron corpus and then I pipe it through a whole bunch of different functions. I do, and they're all are TM map and then some particular like name inside that will operate and do the particular function we need done. So what I've done here is said enron corpus. First thing we're going to do, content transformer str to lower. String to lower is a stringer function that changes things to lowercase. This will go into every email in this corpus. And I remember the corpus is like this complex list object. We can't just use dplyr syntax because it's this really complex set of lists and things. So we're wrapping these sort of dplyr and stringer style things inside these TM maps because it takes care of running it for us. So I'm going to change them all to lowercase. Then I want TM map remove words. The words I want to remove are a list of English stop words built into TM. So it's a database that already exists of stop words, generally considered in natural language processing to be useless. We've got rid of them. Then TM map remove words, remove these specific words. So I want to remove certain email addresses and header information that wasn't removed by default or were not stop words, right? You could have to remove a lot of stuff sometimes, but this is sort of an example. Then I'm going to remove punctuation. I'm going to remove numbers. I'm going to strip all the white space. And then I'm going to stem the document, so take them down to those stem words. Normally, this is the order you would perform these operations in, at least according to the different text mining tutorials and things that I read. I went to a bunch of different people who are natural language processing people in R, and I used the same order of syntax that they use. In tidy text, this stuff might be a little bit more straightforward or may even have forced order to it. So if you work with that, you'll see. Okay, so we've done that. So what the hell does it look like? So what I did is I loaded this package, word cloud, and then I just got a word cloud of the actual words produced by stripping all this stuff down. So enron stripped, I said, give me a word cloud of words used at least twice, and I only want a maximum of 80 different words. They're bigger if they were used more often. Enron was an energy company in California, so you'd expect things like power. You see energy here is the stem for all these different words involving energy. You see R here is the stem for all sorts of different like electricity, electric, all that kind of thing. So these are the stems, most commonly used ones in these emails. Okay, so this is what our data kind of are actually looking like. It's a series of these words, but it's the words in all of these different emails. They're still in those emails. They're not just like a big lump of them hiding around. Okay, so maybe we want to use this in some particular way. So what we're going to do here is we want to filter down to emails that have the term California in it. So what we're going to do here is write a quick little function that will take the content of the documents, look for any instance of California, convert all to lowercase, so it's going to be lowercase California, and then use it with text mine filter, which is sort of a filter command like dplyr's filter, but it works on a corpus. So I made this function doc word search, which is a function X. You're going to give it basically the corpus or data that's going into it. Pattern, and the pattern is going to be based on a search using stringer string detect. It's going to search in the content you give it for whatever pattern you give it, and it's going to be in an any function. So it's going to look and it's going to detect, sometimes you might find California like 10 times in an email. You want this whole function to return true just once if it detects California once or more times in an email. Thus I use any. Then I'm going to take enron stripped, pipe it into TM filter, which is basically a text mining version of dplyr's filter. Then I'm going to say doc word search function, pattern equals California. It's going to filter down these emails, and it's going to find only the emails that contain California. And I see length California emails 14. There were 14 out of these 100 emails I have that had the word California in them. Okay. So we might want to look for patterns across documents. If we want to look at patterns like the correlation, like you say, if there's one term in a document, this other term also shows up in documents, we can do that by creating a term document matrix. This is going to be a matrix of all the terms and then all the documents that we have to see where they occur. To do this, we take the corpus we've created, which was enron stripped, and use the function term document matrix. And then this is what it looks like. this doesn't seem that useful. You can look at this and be like, what the hell is I? What the hell is J? What is V? The number of rows, number of columns. There's a list of terms here in documents. You're like, okay, I don't know what's going on here. But if we subset this thing, we can see what this actually is and how it's useful. We can use the function inspect on that term document matrix, and I'm just going to look at the first 1 to 5 rows and columns of this particular thing. Now we see something interesting. So our rows here are the individual stem terms that might occur in a document. There's like 5,600 unique terms that appear in these emails. They're just sorted alphabetically. Then these are the individual emails, which are just a given number .txt. So we see here that in this email, 114495, the stem abil, so like ability or something like that, appeared 4 times in this document. So we have a matrix of the count of times these terms appeared in every single document in here, right? Well, that means we can do things like do correlations between different terms. We know that, for instance, like let's say we saw that a bill, when this number is high, there's many uses of a bill. There's also many uses of some other term. We can say that these two things are related in some way or commonly used in the same subject, right? So this creates a giant matrix for every document and every term in here. It's really big. It could be gigantic with something like tweets, but that's how you do it. Okay. So maybe we want to focus on words that appear in lots of documents. So let's get rid of every word that doesn't appear in at least 40% of the documents. So we're looking for the words commonly used in these Enron emails. There's a function, remove sparse terms. You give it your corpus here, or you give it your term document matrix, and then you give it a threshold. 0.60 says I need it to appear in at least 40% of the documents, or drop that term. I inspect it now. We have way fewer terms now. We now have 11 different terms. So out of these 100 documents we have, only 11 terms appear in at least 40% of the documents. And they're things like bit, document, folder, forward, Stephen Keen and things associated with him. That's either somebody who sent or received a lot of emails, or maybe he's an executive. I actually meant to Google that and see. Thank and will. And you can see some of these are used tons of times in these documents. Will was used 19 times in that document. So on. Yeah. So this is how you'd find like commonly used terms or emails where a lot of these terms are used. So we might want to make a term document matrix that focuses on words in a particular dictionary and just look at the documents that contain those words in the dictionary. In this case, I've run inspect on the term document matrix of Enron script that contains the words in this list. Where this dictionary is, I want to see the emails that contain California, Utah, or Texas. Then look at the first 5 columns. So we have these terms, California, Texas, Utah, and these emails. And we can see that California was used in these emails, and none of these emails at all had anything from Texas or Utah in it. So you could search for specific terms. You could give a huge vector for that dictionary. You could give like a full dictionary that has all sorts of terms. If you're searching things like tweets, maybe you want to have that vector contain all of the different ways people could write like Trump or insulting names for Trump or whatever you want like that if you want to get everything. That's really common with like looking for public figures that have lots of nicknames or something like that. You want to get all that stuff. Or maybe it's like you have a dictionary that's lots and lots of hashtags or something like that. Same thing. You can get all of them this way. Okay. So maybe we want to find what are the most frequently used words in this corpus. I say here, which terms appear at least 200 times? So I go in this Enron term document matrix, find frequent terms. 200 is my cutoff. All of these appeared at least 200 times in this corpus. Pretty simple function, but shows you what are essentially the most commonly used words in these. Might be really useful for tweets if you wanted to say you got 1 billion tweets. Let's see what the most commonly tweeted about things are. Okay, so maybe we want to know something about like associations between words. In this case, I want to know what words co-occur frequently with California. I just say find associations, our term document matrix. The word I want to find associations with is California, and then 0.9 being like Does it occur with the word California at least 90% of the time? And then here, we see that whenever people use the word California, these are all 1.0, meaning every document that had California had citizen, consumer, all of these STEM words. That's how you find associations between things. Okay, so what else might you guys do? Other things you want to do, if you really want to get into text mining, you might want to use the tidy text package, which is a way of working with text data, things like tweets and all that kind of stuff, that works instead of with lots of lists and stuff, purely in data frames in sort of a tidy way like we've been doing up to this term. I'm just beginning to familiarize myself with tidy text, so I can give a lecture on it. But it looks like the future might be in tidy text rather than TM, but the principles and the terminology are all the same. You might want to do things like make visualizations of word frequencies or those relationships in ggplot. You might do things like use hierarchical clustering to group terms together to see common terms that go together to create things like subjects people might be talking about. You might fit topic models to do that sort of thing too. There's classes that do stuff on topic models. I forget, there's some text mining oriented classes. You might use things like the NLP package, the natural language processing package, to find bigrams, which are two-word phrases that go together. You might use packages like QDAP or TidyText to classify document sentiments, like positive or negative sentiments, but there's other types of sentiments other than like emotional positivity and negativity. There's also domain-specific types of sentiments. Like, for instance, if you work with financial documents, the term risk isn't a negative thing, it's a neutral term. You might load a financial document sentiment thing and do sentiments specific to domains. It's a pretty deep area. So a key thing that I always want to mention is that before you do any research with social media data, scraped data, always make sure that you're legally permitted to do so before you do it. So some networks, cough, Nextdoor, specifically ban any kind of collection or analysis of data, and they may be very eager to sue you if you attempt to do analysis on their data. A lot of those companies have a lot of money and a vested interest in making sure people do not do analysis of their data. Due to the sheer number of closet racists in Nextdoor, they do not like people doing analysis of their network data, or their data, especially because everyone uses their real name and real address on Nextdoor. You can create a pretty good racism map with Nextdoor data, but they make it clear that they will absolutely sue you if you scrape data from them. And also, pretty much all websites will eventually block you if you scrape lots of data, because they can see where traffic is going. And if they see in their bandwidth meter that there's one IP address in Seattle pulling down like a constant 10 megabit feed of text data from their website, they will go ban, and they will ban you. This will happen. So, ethics and sometimes technical considerations. Okay, if you want to get real serious with text mining, which is something you'll probably do if you get into heavy social media data, if you want to do that, I would highly recommend that you check out the Text Mining with R book. It's written by the authors of the Tidy Text package. Like R for Data Science and Advanced R linked off of the course webpage, Text Mining with R, the entire textbook is online and it's free. You don't have to buy it. You can get a print copy if you want. O'Reilly has it print. Everything is free and online. It's formatted in Markdown exactly the same way as R for Data Science and Advanced R, with all of its examples and everything. It shows a tidy coding approach to doing text mining using all sorts of real data, both social media type data and like emails, written type data. I think there's some examples using poetry and actual book analysis type stuff. It looks great. So I would take a peek at that if you want to do it. We're in this great age where so many of the technical documents and things to learn how to do this stuff is all just becoming free, often by the people who wrote the software to do it. So there's really no better place to go. There's no reason to buy textbooks to do most of this stuff anymore. It's all going online for free, which is pretty neat. Okay, that's everything I've got for today. So if you guys have any questions, let me know. Otherwise, get out of here.